not working again. My class, you have to come next. Okay? Sorry. I have reported it, but... My name is Michael Matthews. I'm lecturing in our Alexandria Lecture Theatre. I haven't been able to get the linking to work for about a week and a half now. I just wanted to try recording it over the phone instead of recording it via email. Yeah, well, I think I'm the highest lecturer in here for today until 1 o'clock. So if you don't mind coming at about 1:45, and maybe we can try and figure it out. Thank you. Bye. All right, sorry for the delay. All right, so now that we're finished with basically looking at integrations of single variable and doing definite and indefinite integrals, and the first lecture I went through basically the formal mathematical definition of an integral is as a Riemann sum, where we imagine slicing it up into little areas. As I said, that's the only thing you have to take away from that, that it's the idea of calculating the area is like you take lots of sums in the limit that there's lots and lots and lots of little rectangles. That's what the integral is formally defined as. You can prove all of the things like, you know, the fundamental theorem of calculus and things like that from that idea from first principles. We don't normally do it. So the only reason you would do it that way is if you're dealing with really weird functions. So I just sort of gave you the idea and showed you some applications of it, so to find the length of a curve and volumes of revolution. But I'm never going to get you to do a Riemann integral from first principles. I just simply do not see the point, especially not in first year. All of the functions we're going to be dealing with, we can handle normal ways. So anyway, it's in the unit reader if you're interested. What we're going to spend the next couple of lectures on is this logical extension of this idea to functions of several variables, mainly two. Again, that's so we can visualise what's going on. So you remember that basically the motivation for a definite integral, although we've been concerning ourselves mostly with indefinite integrals, actually doing the integration rather than calculating areas and things like that. But essentially a definite integral is motivated by the area. Find the exact area bound by a function of a single variable in the x-axis. Now this has a logical extension to functions of two variables. In this case, a function of two variables defines a surface. And in this case, we want to answer, how would I calculate the exact volume bound by a surface that sits above some region in the xy plane? Right? Because remember, in function of two variables, x and y are acting as our independent variables, and z's like the height, either above the xy plane or below the xy plane. So to do that, we introduce the concept of a double integral. And first off, we'll just do the case where the region we're integrating over is just a nice simple rectangle. Right? So in other words, say I've got some surface, z equals f of x and y, and I want to be able to calculate the exact volume bound by that surface and this rectangle in the xy plane bound by x goes from a to b and y goes from c to d. Right? And that's the question I want to pose. Right? Now, with functions of a single variable, we also now have the case where, same terminology, if the surface sits above the xy plane, we say the volume is positive. If it's below, the volume's negative. If we march in the negative x direction, it's negative. We march in the negative y direction is negative, but if you march in both negative directions, a negative times a negative becomes a positive. So usually you have to worry about these sort of things. We're not going to. Right? Basically, I'll give you ones where essentially I'm asking you just to do the mechanics of the double integral. If you actually want the volume, you have to make sure it sits above, and you know that one, we can use plotting things to do that if that's the question we're really interested in. All right, so basically this is what how do I calculate the volume of that solid? All right? Now what we can do is we can use the same idea with Riemann sums. This is all the theory behind it. Bugger all that, this is what we're doing. Right? Now with Riemann integrals, what we do is we imagine for a function of a single variable, imagine we've got some curve and we slice it up into little rectangles. Yeah? That's basically what this was doing. And it makes sense, doesn't it? Right? As the rectangles get thinner and thinner, there's a lot more of them. In the limit that they get infinitely thin, there's infinitely many of them. That's the exact value of the integral. Same thing here. Instead of rectangles, though, we use rectangular cubes, basically. Rectangular boxes, whatever you want to call it. Right? So you can imagine I could approximate this thing. Now I know this picture's not showing up too well in the right, but you sort of see what I'm basically finding the volume of all these boxes, and I add them all together. The more boxes I use, the better the answer becomes. So as the boxes get smaller and smaller, in the limit that they get infinitely small, I sum infinitely many volumes. That is the double integral. Right? And that's how I calculate the volume to give of this solid. Right? Now, of course, just as with functions of a single variable, we don't want to do it from first principles because that's stupid. Right? What we do is we use what we already know about integrals of a function of a single variable. Right? So this is the formal definition as a Riemann sum. So this is basically the volume of a particular one of these particular cubes. Say, you know, that it's that length delta x, so some x length, delta x times delta y times the value of the function at some convenient value of x and y. Basically, this bit's the volume of the box, right? And you sum them in the x directions and the y directions, right? As the boxes get infinitely small, the sum becomes infinite. That's what we call a double integral. And this is how we write it, right? So we use two integral signs to say double integral, right? So this gives a volume, not an area. So the double integral of a function of two variables, and notice the change in notation. We write an r initially. We write an r, so this is the easiest to read this out in words. Find the double integral of the function f of x and y over the region r in the xy plane with respect to an area element, which is either dx times dy or dy times dx, because it makes no difference. Right? So this thing here is the area element. So basically it's one of these little squares, right? So this is like delta x times delta y. In the limit that the squares get infinitely small, that becomes dx times dy, or alternatively, dy times dx. What we'll see is that we can do these integrals two ways, right? And the order, in theory, doesn't matter, right? We'll get to that in a sec. Right, but this is the notation. right? Now, if the function sits above, it's actually the volume, and if it sits below, the volume will become negative. So just because your answer is negative doesn't mean anything's wrong. That means the surface is just dropping below the xy plane. So it's exactly the same thing as we're used to with functions of a single variable when you calculate areas. Well, that's all well and good, but how do I actually do this integral, right? Well, it turns out that there's a theorem called Fubini's theorem which tells us, and the proof of this using Riemann sums is in the unit reader if you're keen, knock yourself out, right? It's tedious and silly, and then we turn around and say we never do it this way, right? That's why I don't cover it, right? Right? Now, as I said, the symbol dA is the area element, which is either the x times the y or the y times the x. It makes no difference, right? But Fubini's theorem, which we've got here, says, let's say we've got some function z equals f of x, y, and I want the volume, right? And I use the term volume loosely. If it sits above, it's positive, below, it's negative. The volume, which is given by this double integral, and the region I'm integrating over in the xy plane for the moment is a simple rectangle where x goes from a to b, and they're constants for the moment, and y goes from c to d. Then what Fubini's theorem says is I can calculate this integral these two ways. These are called iterated integrals, and what it's telling you, normally the brackets are omitted, right? But it's one of those things that are implied, but we usually leave them out. Right, let's break down what this actually means. Right, so the above theorem also says we can compute the integral as two separate integrals. We do them one after the other. And the order, in theory, is free for us to choose. Okay? Now, what the first one is saying, basically the way we do this is we work from the inside out. Right? And we do the opposite of partial differentiation. Call it partial integration. There's no such thing, but right, that's the same idea. When we find a partial derivative, let's say I've asked you to differentiate the function x times y. If you want the partial derivative with respect to x, you imagine that's a constant times x, off you go, right? And you integrate as normal. Or if you want the partial derivative with respect to y, you imagine it's a times y and differentiate as per normal. We do integration the exact same way. What this first bit is saying is that you integrate the function with respect to x, imagining y is a constant. Right? So if I asked you to integrate the function x times y with respect to x, that's just a half x squared y, because the partial derivative of a half x squared y is x times y with respect to x. Right? So you do exactly the same thing. Right? Then once you've worked on this inner integral and applied the limits, remember these are definite integrals. There's no such thing as an indefinite double integral. No such thing, right? These are all numbers, technically volumes, but it depends if it's above or below the x-axis. Now when you think about it, when you do this one with respect to x, then apply the fundamental theorem of calculus, between x equals a and x equals b, you'll be left with only a function of y. All the x's will be gone, right? Then you do the outer integral. Then you integrate what you're left with respect to y, where y goes from c to d. So your final answer is always a number. There's no such thing as an indefinite double integral. These aren't functions, these are numbers. The second one is saying you do it the other way. You can also do it the other way around. You could first integrate with respect to y, then with respect to x, right? But notice the order, the way we do these things. So we work from the inside out. So this is x, so these are the limits of x. This is y, so these are the limits of y. Notice in this case the limits are swapped around, right? Right. So, and usually the brackets are omitted, right? Right. So this one's saying y goes from c to d, x goes from a to b. So you see, you sort of work. They're nested. You work from the inside out, right? So the order's important. Right, and that's basically what I'm saying there. The first double integral says first integrate with respect to x, imagining y is a constant, then integrate with respect to y, and you work from the inside out. The second one is saying integrate with respect to y first, then integrate, imagine x is a constant, then integrate with respect to x. Right, because once you've done the first one, all the y's will have disappeared. Right, and then you work from the inside out. Right? Right, Fubini's theorem also says that the order doesn't matter, right? And this can be useful. This means that we can be clever with how we integrate things. right, we can save work. Sometimes it'll be the same amount of work each way. When we do integrals over more general regions in the next lecture, sometimes one way will be impossible for you, right? I could do it, but it will involve functions we haven't heard of, that you haven't heard of, right? But we'll talk a bit about that more in the next one. And notice that also brackets are generally omitted. But if I ask you, say, to do this is telling you a lot. That's saying that I want you to integrate first with respect to y, then with respect to x, and y goes from c to d, x goes from a to b. So take note of the order that I'm giving you the question in, right? Right, and then this one is saying the same thing, just the other way around. So we generally omit the brackets. Right? When we do an example by hand, I'll show you some tips and pitfalls about common mistakes that you can make with this. Oh, actually, here we go right here. Now, I'm going to redo this one by hand. This is one of those things that you see it done by hand. Makes life much easier. So, I mean, you don't have to write this down because it's already there. Let me just show you some tips about how I do this. Right. That's a bit small. There we go. Right, so what have we got here? We've got to, basically I'm asking you to do a double integral of and R is the region where x goes from 1 to 2, so it's just we're just doing rectangles for the minute. Right? So this is saying find the volume, and we use the term volume loosely, remembering it might be positive, might be negative, whatever, of the surface x squared plus xy that sits above or below, depending on the, above the rectangular region in the xy plane. X goes from 1 to 2, y goes from -1 to 1. Now this can be done either ways. Now in the lecture notes, I do it first with respect to x, then with respect to y. I'm going to do it the other way around. Right? So let's say I've decided to do it from y first, then x. Right, so I'm going to do y, then x. So the order you write the dy dx or dx dy is important. And you work from the inside out. So the inner limits are the y limits, because that's what I've decided to do first. And then the outer limits are the x limits. Right? And you work from the inside out. Right? So when I do the first iterate, I haven't touched the outer integral yet. Right? What I then do is I'm going to integrate this with respect to y. So in my mind, I imagine that's a constant plus a constant times y. Right? Imagine the x is a constant that comes along for the ride. So hopefully without too much thought, you get that, right? And you can check your answer by partially differentiating that. If I ask you to partially differentiate that with respect to y, you get back to the previous step, don't you? Right? Again, I use square brackets just like I do when I'm doing the fundamental theorem of calculus, as with definite integrals. I don't care for curve, whatever the frick, I don't care. Right? I just use square. The first common mistake that students make is you now mix up the variables. We are doing a definite integral with respect to y. Right? So instead of just writing that, right, which is what we normally do, but then you look at it and think, oh shit, oh so bother, which one am I doing this with? So what I do, especially when I'm first starting this, is make it clear which variable I'm plugging in. Right? So you are leaving the x's alone for the moment. You're not doing them yet. That's the next step. Right? So what you've basically done is this. Right? You work from the inside out. Then fundamental theorem, evaluate this at the upper limit. So at y equals 1, you get x squared plus a half x. Minus this evaluated at the lower limit. right? And when you've done this step, there should be no y left. That's the point. Your final answer in these is not functions, they're numbers. Yeah? All right, so clean this up. What do we get? As always, careful with the signs and things and the power. All right, we basically get 2x squared dx. All right, now finish it. Now do the next step. Now we're back to a function of single variable. At this step, I mean, you could put, right, that's fine, but I would usually not bother. I've only got one variable left, I ain't going to mess it up. Right? So I just do that here, because the most common mistake is if you replace, you know, the x's instead of the y's, you've stuffed the whole thing up. Right? And of course your final answer then is not going to, it's going to be a function, which it can't be. There's no such thing. Right? No such thing as an indefinite double integral. So what do we get? We get 2/3 times 8 minus 2/3 times 1, and so 16 on 3, that's 14 on 3. Right? So that's the volume. Right? Now, of course, you can do it. Doesn't matter which way you do it. Right? There, I did it with respect to y first, then x. Here, I do it with respect to x first, then y. Of course, the intermediate steps are different. Right? Right? So if I now integrate x squared plus xy with respect to x, that becomes a third x cubed plus a half x squared y. Imagine y is a constant. Right? And notice in the lecture notes, I haven't put x equals 2x equals 1, but when I do it by hand, I do, until I get the hang of it. Right? Actually, I still do it, because I always stuff this up. Right? Upper limit at x equals 2, clean it up, then do the integral with respect to y, and of course, same answer. Right? So the order doesn't matter. As long as you can do the integral, the order doesn't matter. But this means you can be clever with how you choose it. Now, this way, right, compared to, oh, whoops, sorry, wrong button. This way, about the same. This way is probably a touch easier, isn't it? Right? But they're about the same, right? But they're about the same, but this is a good way to check out. However, when I ask you to do, you do not have to do it both ways unless I ask you to, right? But if you've got the time and you can do it and you can actually do it the other way, because when we do integrals over more general reasons, we'll find that there are things that we can't do, that you can't do one way, but the other way you can, right? And so we can reverse the order of integration when we need to, right? But for the moment, we could do it either way, and sometimes when you get the hang of it, you'll find, this way's easier, right? Or this way's going to be faster, or something like that, right? Now, there's a couple of examples in here, but you see, just like with the mechanics, I mean, I think you'd all agree now, the partial differentiation is just as easy as ordinary differentiation, it's just more work, you know? You'd probably agree with that, wouldn't you? Same deal. It's just as easy as normal integration and finding areas, there's just more work, double the amount of work as it turns out. Right? Same with partial derivative, double the amount of work, that's all it is. But all of the things you're used to doing still work. Okay? Now there's a couple more examples in here, and then I want to do another one by hand, which is from your practical sheet next week. All right, so here, this one, we've got this one, and I've actually done it, and notice how so I don't stuff it, because I used to stuff this up every frickin' time, which stuffs up your whole answer. Or you get down the answer and there's still a y or an x hanging around and think, what, did all that frickin' algebra for nothing, you know. Right, so I got in the habit of doing this for the first iterate, so I keep track of what I've integrated with respect to. I mean, you know what maths is like when you do really long problems. You're working through and you start, what the hell am I doing again? All right, we all do that. All do that. All right, this one, I've done it the other way, right? About the same difficulty. So which way you do it wouldn't matter. Here's another one. I've done it both ways, right? About the same difficulty. Yeah. But sometimes One way will be much easier than the other. And sometimes when we do general reasons, one way will be impossible. Now this is a question from your practical sheet not next week, you know, whenever after the whatever. All right? You don't have to write it down. Let's say I asked you to integrate where R is the region the rectangle x goes from -1 to 1 and y goes from 0 to 2. Right? Now normally the choice of which way you do it is up to you. Which way would be easier? Which way do you reckon? Should you integrate with respect to x first or with respect to y first? Which way would be easier? Why? No, as in, not why, as in...
because we don't have to, if we integrate with respect to y, we have to integrate y e to the...
If you integrate with respect to y first, you've got an integration by parts, right? But you will if you integrate with respect to x first, you might still have an integration by parts, but you might not, right? And this is a skill that comes with practice, but the first step is the hardest one because you've got other variables coming along for the ride. Make life easy, right? So if you integrate with respect to x first, you're integrating e to the bx or whatever the hell it is. A constant times e to a constant, that's easy. Right? And when you get the hang of it, if I do that integral first, the y's will disappear. Right? So the last iterate also won't require an integration by parts. So there's a very clear way that's much easier in this one. So easy way. So I'm going to integrate first with respect to x, then y. So if I do the first iterate, this will become, now the integral of e to the xy with respect to x is imagine I asked you to integrate e to the 2x. Hopefully by now you can tell me that's a half e to the 2x. Right? If you need to do the substitution step, do it. Right? And the good thing about this one is this evaluated at the upper limit minus this evaluated at the lower limit. Also easy to integrate, isn't it? Right? Then I can do the integral with respect to y. You know, notice I dropped the y equals because no confusion now. And you do this, what do you get? You get e squared plus e to the minus 2 minus 2. Right? Done. But if you did it the other way, that's going to be a lot more work, isn't it? All right? So let's do it the hard way. So the hard way is to do it x goes from 0, y goes from 0 to x. Right? This requires an integration by parts. I'm basically asked what is the integral of y e to the a times y, right? Which I'd have to do parts. Don't do it as quickly as I am. Right? No, I'm not going to do it in my head, I'll stuff it up. uv minus the integral of and of course we've got some limits coming along, don't we? So we get y on x. Something doesn't feel right. Ugh. Oh God. Right, which means you would have to... Oh, that's awful. You have to use parts again. Actually, no, you can't. You can't do that, can you? Why are we... I'm going to cheat. Can anyone see something I've done? Have I done something wrong? It doesn't look like it to me. Y times the exponential of x times y. Integrate that with respect to y. I should have y on x e to the xy minus 1 on x squared e to the xy. I did it right, awesome. 0 to 2. So I should have 2 e to the 2 on x e to the 2x minus e to the 2x over 1x squared plus 1 on... Yeah, now have it. All right, then I'm going to integrate that. How do I integrate that, I wonder? Oh, of course, that's why. Yeah, you can't. That's what I thought. Right, well, let me illustrate this. That's right, that's why I wanted to show this example. I know what I'm doing, right? Now, notice you get to here, right? You can't do this one, right? Because you can't integrate e to the x on x. That's not one I've taught you how to do because it involves a function you've never heard of, right? Now, this opens up the question, though, well, surely, if I can do it one way, I should be able to do this. Yes, you can, but it involves functions you haven't heard of, right? So remember the thing that I'm not only going to give you ones that you can do, right? So when you get to, you're now at a point where you've got something that you can't integrate, right? And that means you swap the order around when that happens, right? Because this is not something you can handle. Notice parts doesn't work here. That's why I was looking at it thinking, what the hell, right? So the first two functions, so this one's is called an exponential integral. We can do the last bit, obviously. And the second bit's, oh, geez, that's an exponential integral by parts. Ooh, awful, right? But let me show you. Let me show you what's going on here. Right, so that's where I've done the first iterate, right? So what we're left with is basically I need to integrate right? Notice it involves a function you don't know, right? Because it's telling me that the integral of that is minus x times the exponential, or with a negative argument, oh, awful, minus e to the x, right? But if I ask this to integrate this between, right, but actually evaluating the damn thing, hang on, let me, right, notice that's the same answer I got the first way, right? Oh, what happened there? What? It just changed the answer. That's impossible. E to the x on x minus e to the x on x squared will give two exponential integrals that cancel. Ah, nice. Right? But anyway, the point is that when we're doing double, they can be done two ways. Right? If you can do it one way, in theory, you could do it the other way, but it might involve functions and integrals you can't do, right? So if you are stuck with one it's really difficult or gives you something that's impossible, you reverse the order, right? As always, I will only give you integrals that can be done. Now, the trick with double integrals that I will pull on you is that I will give you ones that can be done one way but not the other. Right? Not all the time, of course, but sometimes. Right? So in theory you could do it both ways. So being able to set up an integral both ways and being able to do it both ways, you can't just to say, well, the hell with all this crap, every time I'm going to integrate with respect to x then y. That's not going to work, right? Because I'll give you ones that you can only do, say, with respect to y first. So being able to switch the order, right, and do the integral both ways is crucial, right, to be skilled with this. And when we do triple integrals, we're going to find we can do integrals 6 different ways. And I only want you to do it one way, right? But in theory, you could do it 6 different ways, right? So being able to change the order we choose to do the integral is important, right? So I'd like you to make sure you go through these examples, right? And actually work through them and do these ones both ways. Good practice. Right, and remember that the integral with respect to, it's like the opposite of partial differentiation. Call it partial integration, same thing, right? That's not really the right terminology, but that's basically what we're doing. And the last thing I wanted to show is that let's say this double integrals, definite, there's no such thing as an indefinite, so double integrals generalise definite integrals of a single variable, right? So if classic problem you would have done years ago, or when you first did integrals and areas, but is finding the area between two curves, wouldn't you? Right? Let's say you got the function x squared and root x, or something like that, right? This actually, if you've got that's equivalent to a double integral, and the surface you're integrating is the surface 1. That's because when something has height 1, its volume numerically equals its area, doesn't it? Right? Because volume is base times height, base times width. If the height's 1, right, the area of the base is base times width. Length times width, whatever you want, right? If it's got height 1, its volume is numerically equal to its area. You see what I'm saying? Right? So if you imagine that you do these as where you're integrating the surface 1, right? So if the function function of 2 variables you're integrating is 1, this double integral will give you the area of the region you're integrating over. Now, when it's rectangles, it's not so interesting, right? We can calculate the area of a rectangle without using a bloody integral. Right? But when we do the next bit, where we do integrals over general regions, this actually generalises definite integrals of functions of a single variable. Right, so that's what I'm saying here. This double integral be thought of as generalisation finding areas unders or between curves. We're only doing rectangles for the moment, but it generalises functions of a single variable. So if I can ask you to find the area in an xy plane as a double integral, and then you're just integrating the surface 1. All right? But we'll talk a bit more about that in the next, when we do integrals over general reasons. Please have a work through these ones, right, to get practice doing this partial differentiation backwards. Right, and then we'll move on to general reasons, which are the more complicated ones. Right, but we'll leave it there for today. All right, I'll see everyone on Thursday.